Now we head to problem number 5, IF6 plus, a very obscure molecule, but we just wanted to practice one with a charge, and we also wanted to practice one that we have not yet seen the shape for. IF6 plus, cation. We have one iodine, it'll be a central atom. A giveaway is the first element on these kind of formulas is your central atom, even though they're both halogens and they really only want one bond apiece. Fluorine can only make one bond because it doesn't have a D, so it can't make more than that and have electrons spill in. It only holds 8. Iodine, however, is a huge atom, and it does have a D, so it can make more bonds than it wants to. We have one iodine, Roman 7 with 7. We have 6 fluorines, each with 7 for 42. 7 and 42 is 49. By now, you should recognize that an odd number of electrons is not good for having pairs. And when we have an odd number, always double check to see if it's charged. This is IF6 plus. When it's positive, it means that there's one fewer negative electron on there than you would expect. Plus means there's one fewer negative. So we take the electron off, leaving us with 48 electrons to work with. This is IF6 positive. So really our motive in doing this molecule isn't to determine what the strongest intermolecular force is. We really are just looking for the shape here. Why? We already know it is fully charged positive, so its strongest intermolecular force we can go ahead and circle is ionic. Whether it's polar or nonpolar doesn't really come into play here. Likewise, before we start the molecule, this is IF6 positive. They're all fluorines surrounding the central atom, so I can go ahead and circle same atom, which is one of the ways that if you had different atoms around the central atom, we would call it asymmetrical right away. But it's the same atom, so we can't go straight and call this asymmetrical. So let's go ahead and draw this molecule. Again, we're working with 48 total electrons. Iodine will be in the middle. So I'll draw iodine and surround it with 8. So here's the iodine surrounded with 8. This is a positive molecule. It's always good to put your brackets up with the positive sign right there. This fluorine has a pair to attach to. This fluorine has a pair to attach to. So that's 2 out of the 6 fluorines. So I know that I have a pair here that can attach to one of the fluorines and a pair here that can attach to the other fluorines, but I'm short a pair for this fluorine and I'm short a pair for this fluorine. So how do I solve it? I add the pair. To have 6 fluorines, I'm going to need 6 pairs. 1, 2, 3, 4, 5, 6. Now I can attach the fluorines. At this time, it's real easy best to get rid of those pairs and put the lines in, and then surround each fluorine with 8 electrons. We'll take care of that right now. So each of the fluorines have 8 electrons around them. We have 1, 2, 3, 4, 5, 6 fluorines. 6 times 8 is 48. That's the number of electrons we are supposed to have on this molecule. So we have the correct molecule. So now we can analyze the molecule to determine what shape this molecule is. All right, here we go. Let's determine the shape of this molecule. Iodine is our central atom A, and we have no lone pairs on the iodine, but we have 6 atoms surrounding it. So we put a 6 right here in this column, and that puts this molecule in the octahedral family. In the octahedral family, we have 3 molecules it could potentially be. Octahedral, which is a 6-0, square pyramidal a 5-1, square planar is a 4-1. Well, we know that we have 6 atoms attached to it. There are no lone pairs. That makes this one the octahedral molecular shape. Knowing that this is a 6-0, we can go ahead and fill out our VSEPR notation or shape formula, and this is what the octahedral looks like. Atoms 2, 3, 4, and 5 are in the equatorial plane. Atoms 1 and 6 are in the axial plane, so we can get our angles very easily here. The equatorial atoms are separated by 90 degrees. Then the equatorial to axial atoms are also 90 degrees. The axial to axial, they directly oppose each other. They're at 180. We have the same atoms surrounding iodine. They are all fluorines. They are the same atom. So we can't get the asymmetrical that way. And Asymmetrical, the other way you can get to asymmetrical is that our E doesn't equal 0. What E does equal 0 here. So as we go down, E does equal 0. We follow down this line where it says E equals 0. That is a symmetrical molecule. That is a symmetrical molecule. With it being symmetrical, we don't really need to find out the bond types, because if it's symmetrical, even if they were polar bonds, it would take us to a nonpolar molecule. But we already know that this molecule has a charge, so we don't even care about what kind of bonds there are or if the bonds really cancel. This thing's fully charged. It is ionic. That is the strongest pull you can have on intermolecular attractions. And now we're taking a look at problem number 6, bromine pentafluoride. Bromine's the first element listed there with 5 fluorines after it. So bromine will be our central atom. Bromine's a halogen. It has 7. We've got 5 fluorines, which are also a halogen, Roman 7. That's 5 times 7 is 35. We're working with 42 electrons, bromine in the center, so I'll go ahead and get started with bromine in the middle. So here's bromine in the middle. It's time to start attaching some fluorines. Wherever there's a pair, we can put a fluorine. So we've got a pair on this side, we can put a fluorine there. We've got a pair on this side, we can put a fluorine here. We got a pair over here, we can put a fluorine right there. And I've got a pair up here. I can put a fluorine, but we need 5 fluorines on this molecule, not 4. So I don't have enough pairs. So what do I need to do? I have to add a pair. There's the pair for this fluorine. I need to add a pair for this fluorine. And then we would have all the fluorines attached. There we go. There's our fluorines attached. So now we can surround the fluorines, each with 8, and we can draw lines to attach them just to clean it up a little bit. And then we'll check total electrons. If you remember, we were supposed to have 40 total electrons on here. We have 5 fluorines, each surrounded by 8. That's 40. So we have the correct molecule right here. So now what we'll need to do is take a look and analyze this molecule to determine what shape this molecule is. And it is always smart to double check your total numbers of electrons. We have 5 fluorines, each with 8. That's 40. A second ago I said we're supposed to have 40. No. We've got 7 halogens on here. 7 times, or 6 halogens total. 1, 2, 3, 4, 5 fluorines and bromine make 6. 6 times 7 is 42 electrons, not 40. So what do I need to do? I have to add another pair of electrons to the bromine in order to have this correct. This is why it's important to double check your totals. Now we should be ready to go. Hopefully this will be the correct molecule that we need to take a look at. 42 electrons, then we can analyze the shape. So this has 42 electrons. Again, that is how many we are supposed to have, 42. We've got 5 atoms on bromine and 1 lone pair. So that is 6 total things on the central atom. When we have 6 total things on the central atom, that puts us in the octahedral family. The octahedral family has 3 molecules belonging to it. Molecules belonging to the octahedral family are the octahedral molecule. It's a 6O. The square pyramidal is a 5-1. Square planar is a 4-1. Well, we know we had 5 atoms, and we had 1 lone pair left. Here's our 5 atoms, the fluorines. There's our 1 lone pair. So it's a 5-1. The 5-1 puts us in a square pyramidal shape. Here's the square pyramidal shape. Unlike the trigonal or trigonal bipyramidal family, on this particular sequence for the octahedral family, we remove the axial atoms, not the equatorials. So if you remember here in the trigonal bipyramidal family, we started with 1, 2, 3, 4, 5 atoms, and the equatorial atoms came off. So when one atom came off, we had the seesaw. When two atoms came off, we had the T-shape. When all three of the equatorial atoms came off, we had the linear. With the octahedral family, which we are right down here, here's our base molecule. This is the octahedral. But when we get to the square pyramidal, we lose atom number 6 off the axle. So here goes atom number 6. It's gone. Now there's our square pyramid. Square base, there it is. So what are the angles between the base atoms, or the ones in the equator? Those are 90 degrees, equatorial to equatorial. There is only one axial atom, so there's no angle between the two axial atoms. There's only one. But from the axial to the equatorial, we're looking at 90 again. All right, we do have a lone pair. So as we come out of that lone pair square, that lone pair is what determines the symmetry of the molecule. When there is a lone pair, we can't go down to the E equals 0, so we go up to the E equals 0. We start traveling up this line this way. E does not equal 0, it equals 1. If it's a 2-3, which it's not, it's special. If it's a 4-2, which it's not, it's special. It's a 5-1. So we continue on up. Yes, E does not equal 0, so it is asymmetrical. The other way we can get asymmetrical is if the atoms surrounding the central atom are different. Well, they are the same, so we do not get the asymmetrical that way. But we do get the asymmetrical nonetheless because of the fact that we have a lone pair. When we say asymmetrical, that lone pair is on the bottom. There's nothing to balance that atom going up. The ones in the equatorial plane are balanced, but the one that's going up is not balanced. It is asymmetrically shaped. So now we want to find out, is this molecule polar? For the molecule to be polar, we have to have polar bonds. This molecule has fluorines on a bromine. Fluorine sharing with anything is going to be polar. Fluorines 4O, bromines 2, 8. We will subtract the differences right now. Fluorines 4O, bromines 2,8. The difference is 1.2. That's polar. For this class, 0.4 on up is polar, so we can come down here and we can circle the fact that this thing is going to have polar bonds. So the fact that we know there's polar bonds here, the difference is 1, 2. That's polar. 0.4 on up is polar. We've got both of the things necessary for this molecule to be polar. In order for the molecule to be considered polar, it has to be asymmetrical. It is. There's a lone pair. It has to have polar bonds. There are. So the molecule is polar. That's the only way to get to the polar molecule, is if it has polar bonds and it's asymmetrically shaped. In our final video, we will take a look at the last member of the octahedral family. We will look at square planar.